Hello, welcome. This is the AQA AS Physics. This is Unit 1, June 2010 paper. Okay, so I've kind of kicked off the start of it on the board as I normally do when I can't be bothered to start writing it on the board as I'm explaining it. Okay, so anyway, we're told that there's this sodium, that's it. Sodium decays, goes through beta decay, in other words, beta positive decay, in other words, it emits a proton, okay? It emits a proton and, not emits a proton, that's the wrong word, sorry. Anyway, it goes through beta plus decay. And basically, this question is, it says it forms a new nucleus and by releasing a beta plus particle and one other particle which is difficult to detect. Now, it's given you quite a lot of room in 1A if you look at it. Now, the reason, personally, I think they've done that is so you can write out the equation. And if you do write out the equation, which obviously you'll need to a bit later on, well, it'll help you anyway. You could just ignore that if you wanted to or whatever. Okay, so anyway. Sodium decays into this other the atom, which I've just called the atom X, okay, and it releases a beta plus particle. Now I know it's said like that, beta plus, and you think, oh well, therefore that's equal to saying beta 1 0. Well, it's not. That just means that it's because in the inside the nucleus we've got a neutron changing to a proton, so the proton number. Sorry. Sure, I'll sure before I get something in. Anyway, if we look, well, quite clearly, if this is increased by 1, well, actually, no, before we do that, we need to say, well, there's this new nucleus X, and you should point straight away that we've got a neutrino here, okay? But what, I know, it's obviously an electron neutrino, but what type is it? Now, the way I think of this, obviously, we've got to abide by the conservation laws of particle quantum mechanics, okay? So, one of them states is we need to have the same number of particles and antiparticles on either side. Well, that's just an atom, okay? There's no particles or antiparticles. We say it's a particle, but in the sense that we haven't got any, electrons and positrons on the left-hand side. So the number of particles and antiparticles equals 0. There's no more particles than there are antiparticles. They cancel out, in other words, because there's none on the left hand side. So they should, in theory, cancel out on the right hand side as well. So I'm trying to build it up by saying what we've got here, this beta plus is essentially a positron. Okay, well essentially it is a positron. Okay, so therefore that's a antiparticle. So therefore, what we need is a normal particle to cancel it out. Now this normal particle, I'm trying to convey that it is a neutrino because we can't have any more mass or any more energy in a sense. Okay? So it's an electron neutrino, just V8. I know so you can put 0, 0 there if you want because it's kind of, that's the reason it's undetectable because it's almost like it's got no mass at all and anything it does have is very, very insignificant as well. And then it's just a case of filling it out. Now it doesn't ask us to, it just simply says name a particle which is difficult to detect. Well, to be truthful, it accepts the word neutrino, but you should be able to put electron neutrino. So if you put electron neutrino, that's acceptable as well. Okay, so the key word is neutrino. Now the reason they've given us a bit of a gap there, if you go into 1B, it says write down the proton number and nucleon number of the new nucleus. Now quite clearly, obviously, you know that the nucleon number is the number of protons and neutrons. And if you hadn't have drawn this decay, drawn it in the symbolic form equation, it might be a little bit difficult to try and work out. But anyway, what we've got here, well, we need to, as I said, make the number of proton and neutron either side balance. Okay, so we've got added one more proton here, so we need to take away a proton. In other words, protons turned into the neutron inside the nucleus. Okay, so we've got 10 protons, but we've still got 22 neutrons. Okay, so therefore that 1A is saying neutrino. Okay, sorry, just write that down. And B, well, it's asking for the number of protons and the nucleon number in this new nucleus. Now, the new nucleus I've just called X, okay? So, it's just a very, very simple case of, well, what's the protons and what's the neutrons? Okay, well, the proton number is 10. And the neutron number is, neutron number is the difference between the nucleon number, it's asking for the nucleon number, Okay, so the nucleon number is just this top number, it's the atomic weight, if you think of it like that. Okay, so the nucleon number is the number of protons and neutrons, so it's 22. Okay, so that's 1b. 1c, where it says, name the baryon and each of the leptons found as a form of this decay. Now what we've got here is, well, quite clearly the easiest two ones to start off with are the two leptons that are formed as a result of this decay. So what we're looking at here is the products. Okay, and quite clearly this is a lepton and so is that. So the two leptons, because you get two options for leptons, lepton 1 and 2. Okay, so the leptons are the positron, okay, and the electron neutrino. But you go, well, what is the, because it's asked us for a baryon that is formed as a result of this decay. Now we need to think about the decay more clearly when we try and imagine this, okay. So what actually is beta plus decay? Now it might help and it might not just to draw a diagram of this, although I do think you are asked to do that a bit later on in the question if I'm right in saying so. Well, almost anyway. This might be helpful to draw this diagram. Okay, so what we've got here, this is a very basic little diagram. It just shows, it's just a Feynman diagram representing beta plus decay. In other words, a proton turns into a neutron and it gives us a W plus gauge boson, okay, with a beta plus and electron neutrino. Okay, so in other words, alright. Yeah, is it? Yeah, because the proton has turned into the neutron, the proton's kind of gone away, it's been formed, if that makes some kind of sense. So, one sec. Sorry, I do apologise. Probably should have been a bit more, up with it at the moment, but 1 second. Oh, I really thought this would have gone a lot slicker than this. Sorry, I do apologise. Yeah. I thought I don't know what I was talking about there. Because the proton's turned into the neutron, this neutron has been formed. So the baryon is the neutron. So I do apologise, I've not kind of confused myself there. Anyway, 1D is a very, very simple question. It's just one of them things that you need to remember, okay? Now, obviously you can build it up through just looking at your formula sheet and trying to work out, well, what quark goes with what. And that'll become obvious when I tell you the question. But so it's just a case of remembering it. Because they will never ask you, in terms of defining a quark structure, the proton and the neutron, which it asks you to do in 1D, is very, very simple. Now, the ones that you need to know for your AS theory are very, very basic indeed. But obviously, you can choose from a greater selection. But anyway, I'll just tell you the answers and then I'll go through just if you didn't know it, okay? So, the neutron, it's asking for the quark structure, the neutron and the proton. Well, the neutron is up, down, down, and the proton is up, up, down. Now, you should know if it was asking for an anti-neutron or an anti-proton, you would just do the anti of each of those. In other words, if it was asking for the anti-neutron, which would have the same, because all the only difference between the particle and the antiparticle is the charge is reversed. So if it's a positive charge of 1, it's going to be a negative charge of 1. But you have to remember that the neutron is neutral, so the anti-neutron is the same as the neutron. Okay, so hopefully that makes some kind of sense. But the proton, you would just do you do an antiproton, you put a little dash above each of the quarks, okay, so it's the anti version of it. But as I said, something you should just remember. But I'll just build it up in case you didn't know. Okay, so this is how I act. Now, what I'm going to introduce now is just a quick. I think that's the end of the questions, by the way. Is it? We've got some more. Oh no, we've got some more. I'll do it in a second, actually. Yeah, I was going to do it now because I thought that was the end of the questions, but we've still got 1A to go through. Okay, so anyway, in 1A, it gives you a Feynman diagram. It says complete the following Feynman diagram. But all it gives you is just simply the shape of it. Okay, so, second. And at each of the points where you put a letter, you're given here that there's a U. And you go, what the hell? There's no particle that's U. Well, that's because it's asking you to draw it in terms of quarks. Now, what's happening here, if we relate this is for beta plus decay, okay? So it's drawing it in terms of the quarks. Now, if we just drew again, so we can compare what I drew before, it's the beta decay, where we've got a proton turned into a neutron, okay, with the gauge boson of W plus, okay, and we've got beta plus and an electron neutrino. If essentially what this 1A is asking is we need to draw the beta plus decay on a Feynman diagram, and we need to draw it again, but this time instead of drawing it in terms of the actual particles, we need to draw it in terms of the quarks. Now, quite clearly, we've got the positron, and the electron neutrino. They are both leptons. So obviously, what I mean by that is, well, the leptons, but they're elementary particles, so they're not made up of quarks, okay? So we can't split them down into anything else. And the gauge boson, well, we can't draw that in any other form. It's got to be a gauge boson. But the reason why it's put U and not either UUD, you may be going, oh, well, if it's drawn in terms of quarks, then surely we've just stated in 1D that the quark structure for a proton is up, up, down. But it's got its up. Now, what it's saying here is draw the Feynman diagram not only in terms of the quarks and the elementary particles and in terms of the leptons, which you obviously can't draw as quarks because they're not made of quarks. What it's saying here is draw the beta plus decay diagram, Feynman diagram, but in terms of the quark changes. It doesn't say that, it just simply says copy the following Feynman diagram. So it is really quite a nasty question, personally, if you're not too familiar with Feynman diagrams. Okay, so essentially what's happening here, if we draw this diagram again, but fully just in terms of the quark changes, what happens here is we've got a proton, which I'll just replace with up, up, down, and we've got a neutron here, which is up, down, down. And what you can see is we've gone from up, up, down to up, down, down. In other words, the quark has changed, a up quark has changed to a down quark. So therefore, that's what we put there. We put U, D, W plus, B plus, in other words, positron, and the electron neutrino. Okay? Hopefully that makes a bit of sense. Now that's the end of the questions. I just want to add something onto this video, just to go over this, how I just came up with this 1D. So if you get that, that is absolutely fine. You can end the video there. But if you want a bit more information about these little bit quarks, I think I will be doing a proper particles video. If it's not already up, I don't think it's up yet, but anyway, I will be adding to it. So I just thought for the moment, while there's not a particle video up, I've not properly explained in a video yet why we've got these quarks here. Okay, so I'll just do a kind of a quick analysis now. So as I said, this is kind of the end of it. The end of question one, and we'll see you in the next video if you're interested. But what I'm going to do here is kind of a mix of what they don't tell you. Now, if you look in your formula sheet, you will see kind of a simplified version of this table I'm going to give you here. So what we've got here is we've got an up quark, a charm quark, a true quark, and then a beauty, strange, and down quark. And all the quarks on the left have a charge of positive 2/3, and all the quarks on the right have a charge of negative 1/3. Okay, so if you were going to, now obviously you're given up, down, up, top, now the reason they don't give you these truths and beauty in terms of T and B as extra quarks, and the reason they do that is because, well, there's nothing that you can really attribute to them in AS standard, but you can still use them. They're still quarks and they still fit in with all the quantum mechanics principles, obviously, because they exist. Now, the way I think of remembering this, because obviously they don't give it you, is up and truths. They're saying, you can think of it as saying up and top. It really isn't, but it almost is like saying that. U and T. I'm never ever going to ask you what T quark means. You can think of it as top for them, and unless you're going into particle physics, then you think of T as top. If you are, think of it as truths, because, well, it is. Okay, so all these look like they're pointed up. Okay, so up, top. Now, C doesn't really cut the mustard, but you can almost think of it like that. And then you just have to remember that C goes with U and T, and S goes with B and D, because B is bottom and D is down. But obviously it's not bottom, it's beauty. Okay? And obviously the anti of each one of these is just where you take the same quark, but you flip its charge on its head. So all these on the left, if you were to do the antiparticles, they would have a charge of negative 2/3, and if you were to take all quarks on the right and do the anti-quark of them, sorry, anti-quark the other side as well, I don't know, the same particles, the charge will be positive 1/3. Okay, so that's just a bit of a background on that one. Now, as I said, you can use them quarks in your explanations, and they will be accepted because they do exist in the real world, obviously, and you know, just why not use them? This S, obviously, the strangeness of a standard strange quark is -1, and that can change in a decay, you should know. But anyway, that's just a bit of a background on particle physics, why you can just attribute the neutron. Now, quite clearly, you could just say, well, the neutron, therefore, is TDD, or, but obviously they prefer to put UDD because up quark is in your specification, but it's nice to know the other quarks you can use. Okay, so might be a good remember in that table if you want to, obviously. Okay, so that's just a bit of a guide, really. As I said, I will be doing a proper particles video later on, but for the moment, just a bit of background now until I get the particles video up. Anyway, thanks for watching, and we'll hope to see you in question 2. We'll say, waits for me. Fucking hell.